Yeah, thank you very much. You have heard about the structure of NOMAD already a little bit, but actually I will somewhat go back to it and really give you more details in why NOMAD is structured and actually again how it's really structured. So this is called, actually not by me, but by Claudia, but actually I'm following what she tells me, a primer to NOMAD. So very basic. It has to do actually that I really want to emphasize what is now called really open science and still like to convince you to keep the spirit of open science, and you will see what we mean. And then actually talking about the data which we have, and it's really a lot of big data which you see now, and there is actually possibilities that we can get information from big data about patterns in data even without, or even have very little information about the physics behind it and thinking about the physics later. Is this a little bit too loud, or is it actually for me it really has some I'm speaking louder than Claudia is, so for me it sounds a little bit too loud. Anyhow, so let me actually just go with a very basic general opinion which we have actually in what our topic is, namely telling you about the research paradigms, which in fact for me it's fine. I think for you guys it's also okay. Good, thank you. So we want to go actually to where the light is in this big tunnel, right? And so the light is in some way actually coming together with a new paradigm, how to do and how to get knowledge for material science and for engineering. If you just go back in history and how science has evolved, it started for sure with experimental science, and I just have two examples here. One is a candle. There's a very nice Christmas lecture by Michael Faraday in telling actually why the candle has the colors it has and so on. And this is a free electron laser, another little tool which people use now to really look into properties of materials. This is still, so there's something actually which has changed with the meaning of what the word paradigm means. Paradigm is the way of thinking. In the very old way, it was actually meant that paradigm means actually a complete revolution and the old thinking doesn't have any place anymore. That's certainly not true. A paradigm is a new way of thinking. The thinking was not there, but actually everything in the past is still valid. And of course, experimental physics is still actually a very important tool. Then, roughly in the 16th century or the end of the 15th century, Kepler and Newton and a lot of other people, Maxwell, started in fact creating what we now consider theoretical science and having really Maxwell equations which are really very general or this is actually from Gibbs, thermodynamics. So theoretical science really deriving general laws and models came somewhat in this type of period. In the 50s or 60s, molecular dynamics or Metropolis, Monte Carlo, and then also density function theory in 1964 came about and really created something which again was a new type of doing research and getting information, and that is what we nowadays call computational science. We call it also simulations. In the old ways we called it actually even computer experiments. You solve the equations for something which really people could not really measure, and that is now actually a very big paradigm how to and column how to do science. And right now I think we all live in a very exciting time that we all together create a new paradigm. We are creating a new paradigm that doesn't happen very often in your life, I feel, which we call big data science, namely considering that there is information in data, even if you have not, I mean, in the old time you had actually an idea, you wanted to study something very specific. Now you start in looking actually in a more broad way. You collect data and you look, is there information, if there are patterns in this data, and can you learn something from the pattern by using, which some people call machine learning, or actually data mining, compressed sensing. There's a lot of things you will learn during the exercises here, and I think we are still actually shaping this type of new paradigm. So it's an exciting time we are living in to do this. I mentioned before that this is only actually possible because of something which is now called open science, sharing data. And there's a big discussion the last half year. If you look, I have to admit I'm not reading very often Science and Nature, but actually if you look in Science and Nature, they make a big thing in that if you submit a paper, you have to give all the information. And there was some editorial in June from Nature, actually on the website, it's called Empty Rhetoric Over Data Sharing Slows Science. And someone's saying that governments should really force people to do more sharing. There was a little communication on this big thing. This was actually dealing with all the science, from astrophysics to biophysics, that people were keeping the data and not sharing all the information. What we have succeeded, and we means really it started with Claudia and myself more than 5 years ago, I think, in the spirit at least, is really changing this thing in computational material science. And actually, there's another communication now in this thing by Claudia, by Francesc Ilias from Barcelona, myself. Open data is really settled in material theory. And that means more and more people are willing and doing to share their information so that you can actually extract things even if you have not calculated yourself. So in NOMAD we now, and I show you more in a moment, we now have information about 44 million total energy calculations. 44 million, if you just think about CPU time on computers, this is billions, many, many billions of CPU times, which is behind that. And of course, now you have information to really deal with this for many, many different codes. Now, this is so much because actually some people, so in particular actually Stefano Cotarolo, he in America is actually running the biggest database in materials data, is sharing all his VASP data, and actually also Chris Wolferton is doing this. And since a couple of weeks, actually also the materials project is doing that. So basically all the big players are really contributing their information. They all do VASP, so the fact that VASP is so high is just really due to Stefano and these people. So Stefano is here, you will see the next talk will be given by Stefano. But you see actually, and this makes NOMAD so general and so different. NOMAD is dealing with all codes which are having some relevance. We are really trying to get the information out of it to build this database. Other people are just actually dealing with a very close consortium, and they're dealing actually with just actually one or maybe two codes. So this is the web page of NOMAD. So this is the website. NOMAD means, as you know, the Novel Materials Discovery. It remains by now the largest repository for input and output files for all important computational material science codes. And this is what you will really learn here, hopefully, is that it offers a lot of services, helping to advance material science and engineering. So it's for basic science, but actually also for people in industry, and we still have to improve and learn from this. There is a movie which I show you in a moment. There are some examples where this is important. This is just an example motivated by the Siemens company that if you fly actually the airplane turbines are above melting temperature. You don't really want that it melts. So you put actually a little coating on it, and learning actually what coating is good for this. This was one of the NOMAD projects. So let us actually look maybe at this little movie, because I feel it's very basic. So it's really, don't be disappointed that it's too basic, but actually it's nice what the people have done in creating it. So the NOMAD movie, and I think I probably to put the voice. Okay, so this disappeared. I think Hong, somewhat, did you switch this off? Because we switched somewhat some things here. It worked before. Dann würde er das nicht anzeigen hier.
Zeigt er an?
Ja.
Okay.
Nee, wir haben vorhin bei dir umgeschaltet hier, aber ich weiß nicht genau, welcher das jetzt wieder ist. So why is this red? Red means active?
Yes, I think in this
okay,
means
1, 2, 3.
laptop.
Yes, there should be. Okay.
Can you go to where I go? Machst du da weiter und wir zeigen das morgen am Schluss? Oder?
Okay. Okay, so it worked before, but actually no longer. And we show this movie later just for fun. And I just tell you a little bit actually what the message is. So NOMAD, as you have heard already, starts actually with the repository. The repository is a thing where we collect data. Everyone who does a calculation can upload the data there. And we guarantee that these data will be actually kept there for more than 10 years at least. So it's also a nice way. Actually, the way it started was really, again, actually between Claudia and me, that at some point I had really problems in finding the files which a PhD student has done after he has left after 2 years. So now actually everyone can really do this. You upload and you find actually even after 5 years again what you have done.
Okay. It should be working.
Now it should be working, okay. Let's see. Oops.
The NOMAD European Centre of Excellence, your gateway to material science data. This is John, an engineer in the sustainable energy field who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation of electric cars. So what do John and Laura have in common? Well, to achieve their objectives, they both need to use new high-performance materials. So what can material science do for them? The ideal solution would be to provide them with a map of materials where they can identify and select what they need. Indeed, the amount of different possible materials is practically infinite. So what if all materials could be grouped according to their properties and functions? Is this already possible? Well, this is the idea behind NOMAD, the Novel Materials Discovery Laboratory. NOMAD is the European Centre of Excellence for Material Science Data, set up in 2015 to enable the quest for new and novel materials and their properties, and to reveal unknown properties of already known materials. The foundation of this European Centre of Excellence is the database called the NOMAD Repository, which is available to all and based on open access principles. It hosts input and output files of all significant computational material science codes for at least 10 years, for free. It also enables a confirmatory analysis of materials data, their reuse and repurposing. As a NOMAD repository includes extremely heterogeneous data, which do not allow for direct comparison, these are being processed into code-independent, machine-readable and standardized form. This is the NOMAD Archive, which provides the open access data from the repository in an easy-to-use and easy-to-access way. The archive is the base for the NOMAD Encyclopedia, which displays the properties of computed materials based on millions of calculations that have been performed worldwide. Not only does the encyclopedia provide information about known compounds and their known properties, but it also makes it possible to propose a previously unknown material with the desired characteristics for special application, or to bring to light the previously unknown properties of known materials. The NOMAD COE also provides a set of big data analytics tools that uncover structure and correlations in big data of materials. This enables scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus of future studies. As seeing helps understanding, NOMAD is also developing a virtual reality environment to allow for interactive data exploration, training, and dissemination. Clearly, all of this is made possible by the underlying NOMAD high-performance computing platform, which consists of a distributed multi-layered storage system connected to scalable computing capacity. Data is the raw material of the 21st century. If you deal with material science, the NOMAD Centre of Excellence is your gateway. Start using it now at nomad-coe.eu.
Okay, so this is the simplistic description of what we are doing. So we have done this, we have seen that already. So it starts really with the repository. And again, actually, what is really different is that we are not really having data there in the repository. Not just results, we require the complete input and output files. And the reason is to really judge, in fact, for what the calculations is good, and actually where you have to be careful, you need actually all the information. Because we really want also to give a confidence level to data and so on. Currently, actually this was written some weeks ago, actually it's more than 44, actually it's still more, it's not 44 million, I think, total energy calculations. Now the interesting thing is that, and you have seen that already, so it's open access mainly, but actually you can have a delay of up to 3 years if you still actually finishing your thing, and you keep it just really for your group or your friends. But you get actually DOIs, so basically these things are getting citable, which we consider actually very useful. And as I said already, there are a lot of different codes which are served by the NOMAD laboratory, which in fact implies that the data in the repository are very good as a repository. You can check what other people have done, but in fact they are not good for data analytics because they're completely heterogeneous. They have different nomenclature. What we call energy is actually different to what some other people call energy. There's a different energy zero, there's a different energy unit, and whatever. It's an enormous amount of work. So it's very, very good to have a repository, but it's really not good enough for doing science or new type of engineering. And that's why the first year, a full first year of NOMAD was in creating a conversion layer. Fauzi Mohammed, who is actually still at another activity, but coming here also later to this group, did a lot of this in really creating something, a conversion from the data which you upload from different codes to something which we call the code-independent archive. This was work just really that you see the scale of something like 20 people for 1 year. So it's not really a simple thing to do, but it's a lot of work to really look into what different codes really do and what they mean. Now we are having actually so many data, so 44 million total energy calculations means actually billions of information, because every calculation has a lot of data about, say energies and forces and maybe force constants. So we're dealing with what is in information or computer science called the 4V. The 4V is a computational challenge in computer science: volume, the amount of data; variety, the heterogeneity, the form and the meaning of the data, which is what I mentioned already, coming from different codes; velocity, at which rate of speed do new data come; and veracity, the uncertainty of the quality. For NOMAD, if you really analyze where the problems are, volume is not really a problem. We can bring things down actually by compression very, very well. So we will not run into really what I felt when I wrote the proposal. I expected that we will be actually at a petabyte scale within this year. Actually, we will probably not reach the petabyte. Actually, we are much bigger than expected. We are a factor of 10 bigger than expected, but we are still actually much, much lower than the petabyte. So in volume is not really a problem. Variety, I told you, is a problem, the heterogeneity, but in fact that has been solved. So we have this conversion layer that is no longer a problem. It was really a big problem to do. Velocity is also not a problem, because the calculations which we are doing, when people do calculations usually take several hours or weeks even on big computers. So it's not really a big issue to deal with velocity. But veracity, what is the uncertainty of different calculations? A calculation done with pseudopotentials, a calculation with a very short small cutoff or small basis set just to be faster. You want to have this information because it's very valuable, but you have to know actually for what type of questions you can use it. So this is what NOMAD is really doing. But then, of course, the biggest thing also in the things which you will learn here is really the analytics. So get information which is in the structure of data, information which you would not get if you just study 1, 2, 3, or 5, or 10 systems alone. And that was what in this movie was called, and what we call is, can we create a map of materials? Can we really say there are some parameters, physical, meaningful, hopefully parameters, which we call descriptors, and they tell us actually a material behaves this way. And I'll just give you one example. You will see more in I think the talk by Scheffler, by Luca Ghiringhelli, work by these people here. Can we really tell if a material, you could just give me the atoms, right? You give me, it's it's indium and gold. Can we tell if this is a metal or not without doing a DFT calculation or without really doing an experiment? And so what we have seen and created is this type of maps. That everything in the blue region will be a known metal. And you see actually it's described by some parameters, which are parameters coming really from free atoms and actually the unit cell volume as well. So basically, free atoms and the volume tells us, without doing a DFT calculation, this is a metal or this is a known metal. And we are doing the same thing for topological insulators, for crystal structures, and for many, many other things. So in principle, the idea of having a map is possible, and even more, that you can also say there is actually one parameter, which is two if you look carefully, but one main parameter which really deals with the system, that's the volume. And you also see that if you change the volume, things change from known metal to metals, if you just reduce things. So all this is possible in really creating information from the information which we have to information or to systems where we don't have the measurement yet or the experiment or the theory yet, but we can actually predict how these things should behave. So map building is one of the key issues, and you will see this also in the examples which you study during your period here. So if you look what has happened the last 2, 3, 4 years, I think there is significant progress in showing that there are possibilities, but actually these things do not really work as easy as I present them. It's really a lot of work to really do this, and we're still far away to have this really automatic. And in fact, if you also see where are we with our knowledge, and I would say the knowledge about materials, knowledge which you need for in industry, if you want to create a new product, you need to know actually is there a better material for that. Very, very little knowledge is there. And if you really look what we know, topological insulators, at least this is what we did. So for 2 dimensions, experimentally, there's only 7 which are known. We predicted several hundred in having a map on this, and I think Luca will talk about it. Elastic constants from the 240,000 materials which are known, inorganic materials, which are known to exist, only from 200 we have actually a good account of elastic constants, similar with dielectric constants. Heat conductance was the thing which I mentioned in the very beginning, this turbine, where Siemens told us actually they would like to know actually how heat is conducted in different materials. Is there something which is better or worse? Superconductors we probably know. But if you really look compared to the 240,000, for almost every property which we are interested in, if you want to create a new product, the coverage is just less than 1%. So there is a lot of possibilities out there to have actually products which are even better than what we are doing right now. And if you work in industry, you know that actually if there is a new product which makes it to the market, there's always something, a material which has not been known the last 5 or 10 years, or 10 or 20 years. So it's actually, having actually better materials is really the key. Now, let me finish in telling you actually who is behind all this work. I told you always we, and these people have done it, but actually the people behind this work are listed here. These are, I would say, the best computational material scientists in Europe with complementarity. So there are other people maybe in the same field. But everything in blue is actually people who are heads of computer centers. Dieter Kranzmüller from the Garching, from the Leibniz Rechenzentrum of Bavaria in Germany, is coming. He's giving a talk, I think, on Wednesday. Then we have Barcelona. Then we have actually a lot of highest level scientists. So here's another computer center guy, another computer center guy. Dan Frenkel is one of the key people in force fields. He will be actually represented by Gabor Czarny, who's talking on Friday, if I come sometime at the end of the week. And so a lot of really people you see. The whole thing is really managed to some extent by what is called an executive team. Claudia is there, Kimu from a computer center, Risto Nieminen from Helsinki, and of course myself. So this is actually who are the people behind NOMAD. That means actually behind the proposal, but you may guess actually they're not the people who do the work. I mean, actually they had the ideas, they really were involved in the proposal. It's an enormous number of highly motivated PhD students and postdocs. We have them on the web. Showing them here is actually what would be also not really very nice because you can't really show so many. But this work which we are doing has really attracted a lot of brilliant people, and you will meet some of them during the next days in the tutorials. Unfortunately, you will only meet some of them. And the reason is that this is a typical week in Berlin. So the week started actually with the Berlin Marathon, which was yesterday. But actually, there was also an election, which you know. So let's say actually there was the Berlin Marathon. But actually, there's another marathon really going on in the heads of many other people. So I'm just coming from the Berlin Big Data Center. So this is a center which we have in Berlin, which deals with languages, which you also have to know if you really do this work beyond Hadoop and MapReduce. You are really dealing with so big number of data. You have to handle this data properly, and there are experts in doing this. And they just today and tomorrow have actually their evaluation. So actually I was there up to 12 and then came here. So that is a big activity. So some people are there. This is what Fauzi is not here yet, but some people have to be at this evaluation. Another thing which is happening in Berlin in this week, Claudia and I are very active in some activity on inorganic, organic systems. And there is a young researcher meeting just actually happening also during this week, somewhat a little in Schmöckwitz, which is somewhat 10 kilometers away from here. So this is also here. And there is another school. So there's an international Max Planck research school, which the Fritz Haber Institute, where I'm coming from, is organizing on functional interface and physical chemistry. And actually, this is also from this week and next week, and I'm lecturing there as well. So this is just things which happen all in parallel, and that's why, of course, a lot of people who should be actually involved are active in these other things. And there is another thing which really has a result that Claudia and some others have very little sleep at the moment. There is something on future and emerging technologies. So something we are talking about, what you will see, is really data analytics. And we see that data analytics still sometimes takes a lot of time. But we have some ideas to really make this, to turn this in real time, that you really have the data in our repository, and on a real time you can play with this and get maybe in a second or 2 seconds the answer. In complex things, and this is far from doing this. And so there is a smart proposal, speeding up materials data in real time. And the deadline is tomorrow at 5. So you feel actually, tomorrow evening you will see Claudia very happy because she's organizing it. But at the moment, actually, you don't see actually that she's stressed, but actually I know how much she's working. And Georg as well. So this is actually a typical week in Berlin. Maybe next week will be a little bit less, but actually this is how it is. And with this, I really want to say, this is the structure. You will learn today about the repository and the archive. You will hear tomorrow about the visualization. The day after tomorrow, the encyclopedia, which is really extremely important for if you just really want to look in what is there. How can I also really present that? I mean, people from the visualization also having nice presentation, actually how to look at a crystal structure, at a band structure, and so on. And you will learn this as well. It's really the very general thing, probably will be used by most people. But then comes the analytics, which more or less probably experts will use to really find new materials. All this, I think we like to tell you where we are after 2 years of hard work in doing this. So thank you very much for your attention. I hope you will enjoy the workshop. Very important that you enjoy it, because you will only be able to work hard if you really enjoy this. But you have to work hard. If you don't work hard, you will not really be able to understand what we are doing. But really, you have actually a fresh view. I mean, we are getting blind. I mean, we are seeing all these things every day and we don't see the problems anymore. If you see a problem, if you see something which could be improved, please make a note and tell us. I mean, we want to get better, but we need you. I mean, the whole thing is a community effort. And the community has to do this together. So also enjoy and learn, but really try and help us to improve. Thank you very much.